Hi kids, we will be seeing this particular question, how to calculate change in entropy in particular irreversible process. I will explain what is the irreversible process. So there are two vessels, both volumes are same V0 and gas is filled in this vessel with pressure P0, volume V0, and let me say temperature is T0, and there is a valve here, whatever it is, tap or valve. Now gas is filled only in this chamber. Now this entire thing is thermally isolated from the surroundings. So if there is temperature difference, heat won't be flowing. So now what you are going to do is you are going to remove this valve or you are going to open the tap. Then gas will be, this is vacuum. So gas will be diffusing into the chamber, or the other way of saying it is, there is no work done by the gas because it is free expansion. So those things you can manage. There is no heat taken from the surroundings also, there is no work done, there is no change in internal energy. So whatever it is, we can conclude change in internal energy will be 0. The other way of saying it is initial temperature and final temperature will be same. Now once the gas is diffused, it will be occupying a volume of 2V0, but temperature is same as initial. Now by using PV equals to naught, if the volume becomes twice, pressure will become half at same temperature. So we are talking about only initial and final situation, because in between we know only initial situation and final situation. We can't draw PV graph, because if we have to draw PV graph, we need to know pressure and we need to know PV and T properties at every moment. We don't know the properties at every moment because it is irreversible process. So we can't draw the graph. So it's just a rough thing, but we can't draw a graph. Now for irreversible process, we don't know how to calculate change in entropy, but we know entropy is a state function. So if we can create some initial situation like this and final situation like this in any reversible process, then we can use our formula and stuff and we can do it. So let us see how to figure out, or let us see some similar scenario where initial situation in reversible process is like this and final situation in reversible process is like this. So let me talk about that particular situation in reversible process. So here if you notice, this is not thermally isolated. So what I will be doing is I will be moving, I will be putting some wall or whatever it is, I will be moving it slowly. Such that it is reversible process. When I am moving it slowly and where it is not thermally isolated, if there is any temperature difference coming into picture, surroundings will be supplying the heat. Let me say surroundings temperature is T0. So whenever, so surrounding temperature and this temperature will always be same. So finally I can keep moving it and I can create a situation like this. So basically this process is reversible isothermal process because it is happening at a constant temperature. So when we try to plot the graph, then it is going to look like this. This is reversible process, so we can plot the graph, but if it is irreversible process, we can't plot the graph. Now the thing is, this initial situation and this final situation is exactly same as what we have seen there. So we know change in entropy, or entropy is a state function. So if I can find change in entropy for the gas in this situation, it will be same as previous situation. Now in this situation, if I want to use change in entropy, that is dq by t integral. Now dq is du plus dw. Du will be 0 because change in internal energy is always 0 in that isothermal reversible process. So dq will turn out to be only dw. dw is pdv. By using pv equals to nRT, I will be getting p by t is nr by v. N and r are constant. So when I integrate, I will be getting integral from initial volume to final volume, that is V0 to 2V0. I will be getting this as the answer. Now what is this? This is change in entropy of the gas in reversible process, which will be same as change in entropy of the gas in irreversible process. Now going back to reversible process, if I want to talk about overall nature, now this is reversible. Change in entropy of the gas is nr log 2. Now for a reversible process, change in entropy for the universe will be 0. So from here we can understand change in entropy for the surroundings will be exactly negative of this. So in case of reversible process, change in entropy of the gas is plus nr log 2. Change in entropy of the surroundings is minus nr log 2. Overall change for the universe, entropy change for the universe is 0. But if I go back to irreversible process, change in entropy of the gas is nr log 2, which we calculated in the next case, which is exactly same here also. But here surroundings is not giving any heat or taking any heat, so change in entropy is going to be 0. change in entropy of the surroundings is 0. So change in entropy of the universe here is going to be nr log 2 plus 0, which is nr log 2. So in case of irreversible process, change in entropy is starting out to be greater than 0. Here it is 0. So to sum it up, what we have done, we understood change in entropy or entropy is a state function. So in case of irreversible process, it's hard for us to calculate. So we will try to see to reach the final state from this initial state via some reversible process, so that we can use the formula, and we did the same thing and we got change in entropy for the gas is nr log 2. So change in entropy for the gas in both the situations will be nr log 2, but in case of irreversible, change in entropy for the surroundings will be 0. In case of reversible, minus nr log 2. So overall change in entropy in irreversible is greater than 0, in reversible is equals to 0, right.